Now student, let us go for the second allowance that we are having is the machining allowance. The second allowance is the machining allowance. So see here, generally the accuracy and the surface finish obtained during the sand casting is basically poor. So when the component is subjected to its functionality, so it is not getting correct surface finish from the casting process. So for that reason, we have to do some post casting processes, that is a machining process, to achieve required surface finish onto the product so that it can function well onto the field. So that is the reason why this machining allowance is provided. So what is machining allowance? So the machining allowance, by definition, it is an extra material provided on the casting so that it can be removed after the casting process to get the required surface finish onto the component, onto the casted product, is known as the machining allowance. Understood? Simple. This is nothing but the extra material provided onto the casting, and this extra material will going to remove when during the machining operation. That's why we have to use, or you have to provide, this machining allowance. Okay, so machining allowance, how to give the machining allowance? So definitely again there are the external dimensions and the internal dimensions. Okay, so on the external dimensions, please remember I am telling you the rule how to provide the machining allowance, so that in calculation there will not be any kind of confusion. Okay, so shrinkage allowance, we solve the numericals. For the machining allowance also we are going to solve some numerical. So before that, you should understand, on the external dimension or on the linear dimension, the machining allowance should be added, and whereas on the internal dimension, why this is added? Because we are, after casting process, we are going to remove this additional material and we are making to the accurate size. Whereas internal dimension, say this is the bore. Okay, so definitely to give the machining allowance on this, after giving the machining allowance, say after giving the machining allowance, your bore will be like this, and this is the additional material, and you will going to remove it layer by layer, isn't it? So what happened here? Internal dimension we have to be get subtracted the machining allowance. Okay, so external dimension you are going to add, and on internal dimension you are going to subtract. See here, so after giving this allowance, your bore size is going to reduce, and what you are going to do after boring, after casting, you are doing the boring operation, and layer by layer you are go on removing the material, and you will get this required size of the bore. Okay, like this. So that's why the bore becomes negative and the external dimension becomes positive. Let's take the example, you will understand it. Okay, so we already have the example. We'll take the same for the machining allowance. Say after giving the shrinkage allowance, we got the dimension like this. Say this is, say 2040 4.2. All dimensions are in millimeter. What we get? 150.4 something. And height how much? This was 153.2. 102.1. Or directly we'll take the basic size. Say this is 200, 150 and 100. And the bore is 80 millimeters. So all dimensions are in mm. So this was the numerical we taken for the shrinkage allowance. Same we will take for the machining allowance. Only the thing is that what are the machining allowance? On the length, machining allowance is given as say 5.5 mm. On width, the machining allowance is equal to 3 mm. And on cope side, machining allowance is 6 millimeter. And on bore, machining allowance how much? Again 3 millimeter. So any values if you have, you can take, or whatever the given values in the question, you can use that. Okay, so machining allowance for the length, for the bore, for the cope. Cope means what? That is upper flask. So if it is into the mold cavity, okay, so this will be the cope and this will be the drag. Okay, so when you are looking from the front, you can see only this part. So above core, above this parting line, it is a cope. Below this parting line, it is a drag. And however, our part is placed in the drag only. Okay, drag box only. Now, see here. If when I take this length or width or height, this machining allowance we have to add for 2 times. See, because machining is done from this side also and machining is done from this side also. For height, machining is done from this side and from top side also. Even for the height, machining is even for this width, machining is done from this side and from this side. So on every dimension, please remember that you have to either add 2 times or you have to subtract 2 times the machining allowance. Okay. Even you take a cylindrical specimen or component, see, if I provide it on the length, so it will be machined from this side and it will be machined from this side. So I have to add here and I have to add here the machining allowance. So it becomes 2 times. When I go for the diameter, so it is radial, so I have to add or subtract 2 times. Okay, so like that. So see here, so what will be the dimensions? What will be the dimensions after provision of the machining allowance? So let us take the first is our length. So original length is how much? 200 plus now machining allowance from this side 5.5 and this side 5.5, isn't it? So how much? 5.5 plus 5.5. So how much it is? 5 5 is 10 plus 1 11, that is 211 millimeter. This is our length. Second, for the width is how much? 150 millimeter from both the side. From here and from here we are going to add how much? For width 3 millimeter, so 3 plus 3, it is how much? 156 millimeter. And don't forget, these are all external dimensions, isn't it? These are all external dimensions. Then third one is the height. Height is how much? 100. Cope side how much? Cope side they are saying it is 6 millimeter. If not given like a cope side, directly given for the height, again you can add the top and at bottom, that is after cope how much it is, 3 millimeter all the surfaces. Okay, so it is 6 plus 3 millimeter, it is how much, 109 millimeter. Okay, so here they have to mention on height it is also 3 millimeter, then I will take here 3 millimeter. If cope side not given, only height 3 millimeter is given, then top 3 bottom 3 total 6 millimeter we have to add to the 100 millimeter. Okay, so cope side is given, that is nothing but the top side. They have given a different machining allowance on cope side and at the drag side, so nothing to worry. So it is 109 millimeter becomes the height. External dimensions are over. Now see, we are going to provide the machining allowance on the bore. Okay, now here is important thing. Here whether you are going to add or whether you are going to subtract the machining allowance, definitely internal dimension I already told you, you have to subtract so that board becomes small, and after machining you can make it large or make it to the correct size, isn't it? So this 80 mm bore we have to machining allowance radially how much times, 2 times, that is 2 into 3 millimeter, that is 80 minus 6, it is 74 millimeter. Please remember this. And this bore, by doing the boring operation in machining, it get enlarged to 80 millimeter, that is required one, isn't it? So you get the final dimensions as the length 211, the width 156, height 109 millimeter, and the bore dimension you got 74 millimeter. Understood? So this is the way you can provide the machining allowance on a given component. Now I can show you the component after giving the machining allowance. So it becomes 211, it becomes 156, and this becomes 109, and the bore becomes 74 mm, isn't it? So this is about the machining allowance. So please keep it in mind, machining allowance, extra material we have to add it, and this extra material is going to remove after casting process by the machining to get required surface finish and accuracy onto the component. Okay, and the next allowance that we are going to understand about is the draft or taper allowance. Taper allowance. Now, what is draft or taper allowance? Okay, suppose now by taking some example, I will explain it. So suppose this is our mold making, and we have make a mold here by using this pattern. Okay, this is our pattern. So we are making a mold by using the pattern, definitely. Now once my molding is over, now what is the thing, to get this cavity, okay, I have to lift this pattern, isn't it? I have to take out this pattern, and for that reason I have to lift that pattern. Okay, now what will happen in this situation? If I am trying to lift the pattern, okay, and I want to take it out, so what will happen? So this is your mold. You have prepared a mold by using the sand, and this is your pattern made up of maybe the wood, metal, anything. Okay, and you are lifting it. So you can see here, from this point, since you have started the lifting of the pattern up to this point, from here to here, unless it will get free from this mold cavity, you can see the pattern is continuously in contact with from here to here, right? And you are taking it out, and actually this is your mold that is going to get by this molding. So what happened, the thing is that when you are lifting this component here is pattern. When you are lifting this pattern, if you are not provided any kind of draft or taper, so what thing you are observing here, that the pattern is in continuous contact with the prepared mold for this entire height, isn't it? And meanwhile, if the human hand, okay, if the human hands are making the mold, and if human hand have produced any kind of vibration, so what will happen? So this pattern is going to damage your already molded portion in the cavity, isn't it? So what will happen? There may be the damage can be occurred onto the prepared mold, isn't it? So it is quite difficult thing, no? So to make the things easier, what we have done here, so on the vertical surface of the casting, okay, on the vertical side of the casting, we have provided some amount of tapers here. Okay, we have provided here some taper or draft. Now because of provision of this draft, what happened? See, now this is your pattern. Okay, now you just lift your pattern up to a certain height. Say I lifted to this height. Okay, so as soon as you lift your pattern to the certain height, your entire pattern, see, your entire pattern got free from this mold surface, isn't it? See, as soon as you lift the mold, your pattern is totally free from the prepared mold surface, and there is no chances of damaging that mold because of the human hand vibrations, isn't it? So the draft or the taper allowance is basically provided for easily withdrawal of the pattern from the mold cavity. Understood? Why this taper or draft is provided in the molding or onto the pattern itself? Why this draft? For easy withdrawal. Easy withdrawal of pattern from the mold cavity. Mold cavity, the draft is provided or taper is provided. Where to provide? Whether onto the horizontal dimension or in the width direction? No, on the vertical side. Where? On the vertical side. Very important, on the vertical side. So get question for 1 mark. Which one of the following allowance is also known as the vertical allowance? 1 mark question. Which one of the following allowance is known as the vertical allowance? Of course, taper allowance, because it is provided only on the vertical surface or vertical edges of the component or for that pattern. So the withdrawal is very easy without any damaging to the molded surface. Understood? So this is the draft or taper allowance. So basically there are 2 types of drafts we are having. One is the external draft, which values generally from 1 degree to 3 degree we are using, and another is the internal draft, which value we are using from 5 degree to 8 degree. Okay, now let us take one example. So we will take the example from the machining allowance itself. So take the previous example of the machining allowance. What we got here after provision of machining allowance? So width is not important. This is our parting line. What is parting line? Basically the line which separates the cope from the drag or drag from the cope. It is the parting line. Okay, and here we have got our dimensions after provision of machining allowance. So this length was 211 and this height was 109. Okay, width I am not taking, and this phi is how much? 74 millimeter. Okay, so this is the question, and here we are going to provide the taper allowance, and after taper allowance what will be the final dimensions of the pattern you get is need to be determined. So this is a question here, and the drafts, the external draft, you can take it as 1 degree, and the internal draft you can take it as say 5 degree. Okay, so these are the external and internal values are given. So see here, this is the external dimension and this is the internal dimension. Okay, so I am showing you here the draft for the external dimension. So this is a draft we are providing on the external dimension, and external draft is how much? This is 1 degree, and for internal dimension what is taper? It is given as 5 degree, isn't it? It is 5 degree, and we are having the vertical side as 109 millimeter, isn't it? And on that only we are going to provide it. So here after provision of this taper or draft allowance, how your pattern is going to look like is like this, and we need to determine, and this will be in the molding sand. So we need to determine the dimension. This is already length 211, this 574, this 211, and after provision of draft, this is the thing we are going to determine, and this is the bore value we are going to determine. Okay, now let us calculate. So this is 109, say this is the value x, this is value x, so we need to determine the x value here. So this tan of 1 degree is how much? This x divided by 109. So x is equal to 109 times tan of 1 degree. Calculate. Students, please calculate. So this is 109 tan of 1 degree. It is 1.90. So x is 1.90. So here 1.90, here 1.90. So what is the length? So 211 मिलीमीटर की लेंथ अब क्या हो गई? 211 plus 1.90 plus 1.90. So the length will be 211 plus 1.90 plus 1.90. How much it is? Into 2 plus 10 plus 211. It is 214.80 mm. And what is our phi? Bore diameter 74 minus, see here, say this is y. So what is value of y? So tan of 5 degree is equal to what? Y divided by 109. So y is equal to 109 times tan of 5. So 109 tan of 5 is equal to 9.53. So 9.53 from here and 9.53 from here get subtracted from diameter 74 minus 9.53 minus 9.53. So you get 54.9 millimeter. See bore dimension what you will get here after provision of this draft. By the external draft you have increasing the length, that is it becomes 214.80 millimeter, whereas your bore is going to decrease at one end, and here the value of bore is 54.9 millimeter. So this is the taper allowance. Please